Okay, welcome to our third tutorial in the R series. This one's going to be on logistic regression. Hopefully by now you are getting a little bit more accustomed to the interface. There's not a whole lot that's different this week from last week, so you'll find that once you get a feel for the formula interface for specifying your regression models, things basically remain the same. You're just going to use slightly different functions each time, but the output's going to look similar, and even some of the diagnostics. So for this session, you'll need to attach the faraway library and another new um, package, the PROC package. So again, you probably won't have this installed, so you can go to your packages, install PROC, and install it. And I get a message yelling at me because that package is already loaded because I cheated and started. So I'm going to press cancel, but you won't get that message. You should get the nice success message that you're used to. So we're going to start with an example. This is a really cool data set that comes from the book. One of the reasons I chose this book is because it's got some good data sets. And it's a study from the National Institute of Diabetes, Digestive and Kidney Diseases on 768 adult female Pima Indians that were living near Phoenix. And the purpose was to study was to investigate factors related to diabetes. So we've got 15 variables in the data set. Again, you can use the question mark in front of Pima. So if I type question Pima, I get the help file and it tells me what I've got here. So the variable that we're going to be interested in is test. That is simply 0, 1 if a person shows signs of diabetes. I don't know what kind of test it was. It looks like the data were actually from the UCI machine learning repository, so you could go there and find out. In the interest of time, we'll just keep going with it, but you can see things that were collected that shouldn't be too difficult. One of the things that I wanted to do, though, because some of these data were missing, so we kind of do a little bit of work on this data set to get it into the sort of way it needs to be. Now, one thing I want to point out that's important in logistic regression and any kind of regression in which you have a discrete outcome variable, so meaning it can't take on every single value that there is that it works a little bit different in terms of sort of what sample size is best for estimation and to make sure that your model, the results can be interpreted validly. And so it's usually we think about overall sample size as being important, and that certainly is, but for logistic regression, what actually matters is the number of events of ones in this case. So this would be, since we're coding it as a 1 means a person tested positive, 0 negative, then we've got 268 events in our data set. And there's a kind of a rule of thumb, a 15-to-1 rule of thumb, meaning that if you divide the number of events in your data set by 15, the number that you get, in this case, it's approximately 18, means that's how many, you can think about it as predictors, or really sort of degrees of freedom that you can spend in doing the modeling. And the reason I bring that up is often I'll see very small data sets, with 100 patients or something like that, and the person doing clinical research wants to do logistic regression, and they want to control for like every variable under the sun. And that's a great idea. You want to make sure to control for confounds, but you'll end up, in those data sets, let's say maybe there's 20 or 30 events, really only 2 or 3 predictors are going to work in the model. If you start to add more, what's going to happen is you're going to get your confidence intervals for the regression coefficients are going to get larger and larger and larger. Basically, you don't have enough information in the data set to be able to fit that much of a complex model. So we're good here. We don't even have 18 variables, let alone predictors. So that's just a nice thing to kind of keep in mind when you approach analysis in the real world. Now, I've already coded some of this stuff as missing in the original data set. So if we look here now, you'll see it as I fixed it. So there are a number of people that were missing insulin values. They were originally all the zeros that you see here. They used 0 as the code for missing value, which wasn't a great idea. So just a kind of a nice little code lesson. The if-else command in R allows you to quickly test a variable and then do something with it. So what this does is it takes, for each row of the data set, it looks at the value in the PIMA insulin column. And if it sees a 0 there, then the first part of the thing after the comma is what you do, what the function does if this condition is true. So if this condition is true, the output is NA, which is R's native, you see here, missing value value, right? So the placeholder for missing values. The second part is what should be outputted if this condition is false. So if basically what I'm saying is make a new variable, and the values of that new variable are going to be dependent on what is in the values of insulin. So for each, and if we look at the data set here, for each person whose insulin value is 0, the new variable is NA. For each person who has an insulin value that's not 0, it's just copied over there. Right? So it's a little shorthand to make a copy of this variable and set all of the zeros to NA so that we can ignore them. So in fact, if we were to use the insulin variable as a predictor in our model, we'd have fewer than this number of events because we'd lose some people. Just if you want to use any of these other pieces, you've got to do the same thing. So you'll see that you can try this yourself, see what happens. And then, I don't normally do this, but just going to do it just to illustrate it. So it's always a good idea that if you have a numeric predictor that is continuous, like BMI, that's meaningful, is you leave it as a number. Again, a lot of times clinicians and other people like to see these turned into categories because they think that way. And that's great for descriptive tables. But for predictors, for model predictors, you get the same results. And you spend less degrees of freedom by using the continuous variable. So your model is going to be more stable. So just a note on that. So this code here uses the cut function, which takes a numeric variable, and there's lots of different ways to specify the breaks part. But basically, you tell it, where do I put in, how do I break up the numeric variable into categories? So you give it the cut points, and then there's some stuff there that you have to do. And then you can also label the categories there, but it's usually easier to just set that afterwards. So this will make a factor out of whatever numeric variable. And then one thing, so let me show you this actually in the code. So let me back up because this is helpful. So by default, what's going to happen if I run this command, and let's see, I do table. Oops, I want to run this part too. Well, actually, this will be instructive. So let's run that command. Now I'm going to look at the categories and how many people are in each one. You notice that the cut function, the labels that it uses are simply just the intervals that you gave it. So basically, these are what are called half open intervals, meaning that it includes the lowest but not the highest. So these are BMIs from 0 all the way to 18.499999. Then we start with 18.5, go to 24.9999, so on and so forth, right? So those are ugly and not helpful. So if I want to change the levels of a factor, I can do that by using a vector and having the labels in there. Now, they've got to be in the order that the factor's already in. So we've ordered this as underweight, normal, overweight, obese, right? And so I've got to make sure that I label them correctly. Right? So I put labels in for the levels. If I run table again, I see what I hope to see. Now, if I use this categorical predictor in a regression model, by default, what R is going to do is it's going to use it's going to pick the category that is first. In this case, for a factor, the one that's really category number one, which is underweight. You may want to, in analysis, use normal as the reference category. So there's a function called relevel where you can move that around. So I'm going to relevel the BMI factor, and now I can use the contrasts function to show me that, right, normal has zeros on the actual dummy regressors that'll be in the model, an indicator variable for underweight, overweight, and obese. And so now the intercept, or all, basically what I'm going to have now is a log odds ratio when I fit the model. If I use this predictor, that compares underweight to normal, overweight to normal, obese to normal in terms of their log odds of having a positive test. So we'll do some regression modeling. The main thing that's going to differ here is now we're going to use the GLM command. So if I type $GLM, I see that it's also a base function. So now we're fitting a generalized linear model, which is just what it sounds like. Instead of fitting an ordinary regression model with a numeric outcome, the generalized linear model allows us to use other types of outcomes. And what changes is that we have to specify a family, basically a probability distribution or a probability family for the errors. So with a binary variable, which is 0 for no diabetes, 1 for diabetes, your errors of prediction are only going to be 0 or 1. They're going to be binary. So overall, the errors are not modeled as normal anymore. They're modeled as binomial. So that's the family argument. You'll see when we get to count regression that we'll change the family. For logistic regression, it's family binomial. That's what you do. So everything's the same as before. We use GLM instead of LM. And so what I mean is the same is that then we specify our model using the formula interface. So for this to work, the outcome or the dependent variable still has to be numeric, and it has to be coded as a 0, 1 variable, right? With 1 meaning the event happened, meaning that the person is positive for diabetes, 0 meaning it didn't happen. And remember what this GLM actually does is we're modeling the logit, the log odds of a positive test as a linear function, because we can do that of our predictors. Right? So we make the assumption that the probability of testing positive is linear in the log odds, which just means, again, you'll learn some theory about this in the actual course. It's just a fancy way that we can deal with this type of variable. So we're going to model the log odds of diabetes based on glucose, diastolic blood pressure, BMI, and age. So we specify the formula, we specify the error distribution as binomial, and we specify the data set, and then we use the summary command. So I'm gonna, now we're also show you something new this week, which is I'm using R Markdown instead of just a script. So you'll see there's a little play button here, and these are called chunks. And so you can run a whole chunk at the same time. So this chunk just contains these 2 lines of code. So if I press the play button, by the way, in R Markdown, for certain things, the output occurs in both places, both underneath what you see there and down here. By the way, it's what we're looking at is actually how the nuts and bolts behind this HTML. You're seeing it here in Markdown. So just to not make it confusing, we'll look at the output down here in the console. And so what do we got? Remember, for logistic regression, everything is on the scale of the logit, the log odds, which is the logarithm of the odds of a positive response, right? Which is basically the coefficients. When they're positive, it means that there is as the variable goes up, as the predictor increases, if the coefficient is positive, it means that the log odds also increase, and it's a linear association. So it remains the same. So for a unit increase, so as glucose increases by 1 unit, the log odds of diabetes will increase by 0.03. Right? Now, that usually isn't that meaningful for folks. We do see that, not surprisingly, that's significant, probably because the test is based on glucose. So we're controlling for glucose, and then we're testing these other things. So again, diastolic, that's a numeric variable. We see the coefficient is basically 0, so we don't have evidence for a conditional association there. Let's talk about these 3, right? These are the 3 dummy regressors for BMI. So now remember what they are. And again, I wouldn't normally do this. I would just have BMI as a number, but I wanted to show you, what you get here. So each one of these coefficients is a comparison between the category represented by the intercept, which is the one that's missing here. That's normal weight individuals, or healthy weight. Sorry, we call it healthy weight now. So each one of these coefficients is a comparison between the healthy weight group and the group that's specified here. Right? So this represents as you go. So healthy weight, remember, is equal to 0. Underweight, on the underweight variable, is equal to 1. So this says as we go from 0 to 1 on underweight, which is as we go from healthy weight to underweight, our odds of diabetes, log odds of diabetes, increase just a little bit, but we're pretty uncertain about that. So it doesn't seem like we can really say a whole lot about that effect. Not surprisingly, though, as you compare overweight to healthy weight and obese to healthy weight, both of these, the log odds of positive tests are increasing. Again, not surprising. We see smaller and smaller p-values. We're going to see large confidence interval, or small confidence intervals bounded away from 0. So it does seem like there is good evidence for much higher log odds and we'll translate that into odds and probability of testing positive if you're overweight compared to a normal person or obese compared to a normal person. Now notice we don't have any comparisons between obese and overweight or overweight and underweight. We'd have to change up the way that we set up our contrasts if we're interested in that. Finally, again, not surprising, older people more likely or have for each increase in, as age goes up by 1 year, your log odds increase by 0.03. So it's about the same as the glucose effect, also significant. So interpreting a logistic regression model's results, when the results are given to you like this, so the summary command by default, everything's on the log odds scale, but you can interpret them exactly as you would an ordinary linear model because it is a linear model, right? It's just that the outcome is now the log odds rather than probability or whatever else you want. Usually, though, we do odds ratios. So there's a couple of ways to get odds ratios in R. And the simplest way is to notice that if you simply just exponentiate the coefficients, meaning that make them the exponent for the number e, you get odds ratios. Now, often we deliver odds ratios with their confidence intervals. So let me show you this separately. So the way to get these coefficients from the model and do stuff with them is just to use the coef function, coef mod 1, right? Lists them out. Now, if I want these on the odds scale, I do exp, which is the short for exponential, exponentiate coef mod 1. This is what's called a nested function call because now I could do the same thing by saving this, but I don't have to, right? So I can, inside this exponentiate function, I'm calling this. So basically in the background, the coefficients are laid out and then each one of them is exponentiated. Yeah. So I see that. If I want the confidence intervals, I exponentiate the confidence intervals that are come on a log scale. So conf int mod 1 is going to give me the confidence intervals. It uses the profile likelihood method, which you don't need to worry about. It's a little bit more accurate than an approximate method. It's based on the likelihood. You see we have negative and positive numbers, right? Odds ratios can't be negative. So we know this is on the log odds scale. So these gives us confidence intervals for the raw untransformed coefficients. We want confidence intervals for the odds ratio. So the way you do that is that you can simply exponentiate each one of these endpoints of the intervals, exp conf int mod 1. And now I have confidence intervals for the odds ratios. Now, I don't have the coefficients, right? So kind of a quick and dirty, there is a couple of packages that do this for you, but quick and dirty way to do that is to use the cbind command, and then to avoid having decimal points out to 8, I'm going to use the round command, which rounds everything to 3 decimal points. So I'll just do that down at the console so you can see it. And there I go. So now I have the first column are the actual odds ratios and confidence intervals. So remember, the confidence intervals will agree with your significance tests using alpha of whatever we made with, this is a 95% confidence interval, so alpha of 0.05. The null hypothesis for an odds ratio is 1.0. So if 1.0 is not in the confidence interval, you would expect to find, as we do with glucose, that the P is going to be small. So we see that for glucose. We see that for the comparison between overweight and healthy weight, obese and healthy weight, as well as age. Right? And remember what odds ratios are. So there's two ways to interpret an odds ratio. The first is as a multiplicative effect. Right? So for example, if we look at obese versus healthy weight, the odds ratio is 9.029. So let's just round it down to 9. What does that mean? It means that if you are obese, the odds that you would have diabetes, at least in this sample of this test, are 9 times higher than if you're normal weight. So the odds ratio is multiplicative. It's telling you how many times greater are the odds in one group versus the other, right? 9 times greater. Other people like to do the odds ratio minus 1 times 100%. So if we did that there, we'd do 9.029 minus 1, right? And 8.029 times 100. That means that if you were to somehow transform yourself from normal weight to obese, the increase in the odds of diabetes would be 800%. It's an 800% increase. Right? So you'll often hear people use the percent based when you have smaller odds ratios. For example, the glucose one. For each increase in a point of glucose, 1 unit increase in glucose, right? Your odds of diabetes are multiplied by 1.036. It's not that helpful, so we can do, what percent, how much do they change? What's the percent change? So we would do 1.036 minus 1, right? 0.036, easy, 0.036 times 100. So it's a 3.6% increase in the odds, which some people like that better. Okay. So that's the basic nuts and bolts of logistic regression in terms of the output. There's something I'll kind of leave for your reading of how to, 1 unit increase in glucose might not be that interesting. Let's say we're interested in a 5 to 10 unit increase. We simply just raise the odds ratio to that power. So a 5 unit increase in glucose relates to is associated with a 19% increase in the odds of a positive test. Okay, two more pieces I want to show you. One is we can use the drop one command here, and so I won't show it to you in R. I'll just show you that this is the result, just like with ordinary least squares. What we're doing is we're looking at the change. In this case, you'll learn, in the book about deviance versus residual. So in generalized linear modeling, we have to generalize the idea of a regression residual. And the generalization of a residual is model deviance. Model deviance. Deviance is bad, right? Deviance is misfit. So we want models with smaller deviances, just like we want models with smaller residuals. Turns out that models can be compared in terms of their deviance. The difference in deviances between models is chi-square distributed. So we can use a chi-square test. It is actually a likelihood ratio test. That's what LRT means. And this is basically telling us what happens if you drop this glucose variable from the model. If you drop glucose from the model, deviance goes way up. It goes up by 125, and that's a huge increase. So the model gets really bad, like much worse if you drop glucose, not surprising. So overall, there's a glucose effect. These tests are really helpful, and that's why I showed you BMI this way. If all you care about are not the specific contrasts, like comparing underweight to normal, so on and so forth, but just is there variation in the log odds across some number of categories, right? And so you'll see we just have one line for BMI. What does this represent? This line represents a comparison between this model, right, the glucose, diastolic blood pressure, the three BMI dummy variables, and age. So it represents a comparison between this one and one without the three BMI predictors there. Right? So if we drop BMI as a predictor, we drop all the dummy variables, and again, the deviance goes up. It's a significant increase. So again, we would like to keep it in the model. Right? In fact, the only one we can drop and really not much happens is diastolic blood pressure, and of course that agrees with what we see up there. Okay, a couple other things. I wanted to just show you the residuals. It just, you can use the plot method. I'm not going to discuss them because there's a whole week on residuals. They're going to look wonky, basically because you've only got two values of the actual response. So we'll come back to these. We're not going to look at them in the same way. So for right now, just note that you can get them, but you're not going to worry about them. Another thing we do with logistic regression is we use it for predictive modeling. So you've probably heard about ROC, sensitivity, specificity, so on and so forth. That's because we can actually transform the linear predictor, or what we call the logit, into a probability. So here's just some code where I did that. So the person 41 in the data set. So we look for row 41 here. We're going to see a woman who has had a number of pregnancies, blah, 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 blah. It turns out she's young. She does not test positive for diabetes. Right? Now, by our model, here's her value of glucose, her value of diastolic blood pressure, her BMI category, and her age. Now, using our model, we would actually predict that her log odds of diabetes is quite high. And if I want to convert that into a probability, I raise E to that number and divide by 1 plus E to that number. And I end up with actually a high probability. The model would predict a high probability that she would test positive. Now she doesn't. Right? So now the reason I show you that is because the way that logistic regression works is it is a regression. We do predict a number for each person. We don't actually predict a 0 or a 1. We predict a number. That number can be transformed if we want to into a probability. And then if we want to compute sensitivity or specificity of, let's say we were interested in this being a screening test, like we get, or an online calculator, calculate your probability that you would have diabetes, right? Or, basically like put you in a screening stage. We need a threshold, right? So we might need quite a high threshold if this model was to be trusted. We're always going to be wrong about some people. And so, that's fine. So just to show you, this code takes, and I'll show it to you in the code just so you can see what it does in the background. Okay. So here is everybody. So without the missing data, this is all the data in our model. What I'm going to add there is to predict, give the predicted response using a threshold. Right? So now we have predicted probability of each person and their value of the test. So what I need to do is now make a new variable where we take their predicted probability and classify them as 0 or 1. So this does that using the threshold of 0.51, which you can change. So using a threshold of 0.51 for positive, I can see that, right, this person, right, their predicted probability is greater than 0.5, so they're a yes, no, blah, 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 blah. So now what I want to do is go through and create what's called a confusion matrix, which is to cross-tabulate the actual reality, which is the value of the test, right? So no diabetes, diabetes, and then the predictions, right? So basically we've got 426 correct no predictions, 131 correct yes predictions, and then these two incorrect predictions. Sensitivity and specificity are functions of that. And so I'll just leave those there, right? So we've got lower sensitivity but high specificity, meaning that the way, if we use the threshold of 0.51 to classify somebody as probably diabetic, we will miss some people. So our sensitivity is going to be somewhat lower, but we'll do pretty good ruling people out. We won't have very many false negatives. Now that's only for a given threshold, right? If we want to know how good we might do across all thresholds, and by the way, since we have so many different probability values, there's essentially one, a threshold for each person. We can plot the receiver operating characteristic curve, right, or the ROC curve, and we can do that in R. And so this code will do it. First, we actually have to create the data, which is basically just the ROC function computes sensitivity and specificity for the whole data set and stores it in this little thing here. We can then plot it, and we see that it prefers to plot specificity and sensitivity rather than 1 minus specificity sensitivity, but it's the same, right? We would basically, our optimal prediction model is one where we've got high sensitivity and also high specificity. So we would want to pick a threshold that corresponds to somewhere in this area. The area under the curve, right, is a metric which can kind of tell you about how well this model basically puts people in order. If you, the way to interpret this 0.8273 is, if I picked two people at random, one of those people, if I picked a person who actually did have a positive test for diabetes, and I picked another person at random who did not, the area under the curve gives us the probability that our model would correctly classify those two, would correctly tell the difference, would correctly predict, right, that the positive test was positive, negative test was negative, right? So we want this value to be high. The largest it can be was 1.0. 0.8273 is not too bad for a model that's in development, and so on and so forth. So again, there's a whole huge body of knowledge on prediction models. I just wanted to again show you some code that can help you do that. It's also always good to produce a confidence interval for that. All of these functions come from the PROC package, that one I had you try to download before, PROC. There's a really nice open source article that talks about the package, shows you how to use it. It's very well documented. By the way, you can, when you're in here, if you click on this stuff, you can see different things. This is just description file. Sometimes it tells you who who made it. Sometimes it links you to vignettes. So if you click there, you'll see that I don't think it links you to any vignettes, but it should give you, go all the way down the bottom, some citations and examples, and you can kind of run through this. So again, nice thing about R is everything is there for you, open source. One final thing, and again, I'll kind of leave this as an exercise for you guys. You can see it here. There's a lot of sort of critique about the various R squared goodness of fit measures. There is a Nagelkirche pseudo R squared function in R, but this is code that shows you how to reproduce the value of it as it's shown in the textbook. And so it relies on two things, two numbers, the model deviance and the null deviance that are both in your model one object here. So null deviance and model deviance would be right here. Okay? And then we need n, and there's a formula for using these two things. We find essentially, if we kind of can compare this to regular R squared. It's not really a proportion of variance. It sort of is. It's usually lower. So it's 0.39, almost 0.4. Some people like these, some people don't. I figured I'd show it to you because SPSS spits them out. There's some other statistics we'll talk about later as far as goodness of fit. But just because you fit a regression model and get some stars here next to your predictors doesn't mean it's a good model. So it's always good practice to do some of this other stuff, to just make sure that what you're looking at is robust, right? Okay, well that's it for this week. Again, the main thing to care about is that GLM function. So kind of make sure that you understand what's going on there, and we'll go through a couple of other things over the next few weeks of our tutorials. All right, see you next time.